video, we're going to be looking at Module 6 from the OCR specification, focusing on the particle physics, radiation, and medical physics sections. So a few things before we get into the video. There is a link in the description to a template you can use as you're working your way through the video. It's a Word document. And in terms of how you should use the Word document, what you should do is for each section, what you need to do is work your way through it on your own. See, you fill in as much as you can about the things that you should know. And then what we'll do is we'll review that section so you can see what knowledge you're missing. And so this is a process you can go through several times as part of your revision. This is definitely not something you should do once, which is why it's an electronic version, so you can use it a few times. Okay, so in order to help you learn some of the definitions and knowledge, what I've done is I've created a Memrise course to go with the video. And again, there's a link to that in the description, so you can practice your knowledge until you can recall it with no effort at all. Okay, so we're going to start off by looking at the nuclear model of the atom, looking how we discovered the nucleus and some of its properties. So let's have a look at the experiment done by Rutherford and his students Geiger and Marsden to understand the model of the atom. So what I'd like you to do is work your way through section 6.4.1, see how much you can already do on this, and then we'll have a look at what you should have. All right, so I'm going to assume you've paused the video now and have worked your way through. So first thing is they used an alpha source, as you may guess from the name of the experiment, and they placed it inside a box with a narrow slit, and that produced a fine beam of alpha particles that was directed towards some gold foil. The gold foil itself was stretched really thin, so that's why gold was used, because it's really ductile. And the reason they do that is so that each of the alpha particles will only encounter one gold atom or one gold nucleus in essence. So what they then did is they used a detector to identify the paths taken by alpha particles after their interaction and the number of alpha particles that went along those paths. And what they found is a very high concentration of alpha particles were detected behind the gold foil, which means most of them passed undeflected or very minorly deflected, which told the experimenters that atoms were mostly empty space. But the other region of interest were the small number that were deflected straight back. And because alpha particles are positively charged, that meant there had to be a very small region of strong positive charge in order to be able to essentially stop the alpha particle and send it back the other way. All right, so that's how they know about the nucleus. So the image that is then built of the atom is often known as the planetary model. So you've got a nucleus at the center containing your protons and neutrons. And for things with small proton numbers, protons and neutrons are in this similar sort of quantity, but the more protons you have, you then start to have extra neutrons. But that nucleus is surrounded by a cloud of electrons arranged in different energy levels. So this is the picture following the alpha scattering experiment. And from the numbers of particles that are passing straight through or are being deflected back, what they do is they get an estimate of the size of the atom. So the atom they already knew was around 10 to the minus 10 meters, which is known as 1 angstrom. And because about 1 in 10,000 were reflected back straight to the source, they guesstimated that the nucleus was about a 10,000th the size, or 10 to the minus 14 meters, which isn't too far off how big a gold nucleus would be. So that's a pretty good estimate. Okay, so I mentioned these two in passing, so let's define what it is. So proton number is the number of protons inside the nucleus of an atom. And sometimes in chemistry, this is sometimes known as atomic number instead, and you can find it on the periodic table. Nucleon number is the sum of the number of protons and the number of neutrons inside a nucleus. So a nucleon could either be a proton or a neutron. And again, you can pick that up on your periodic table. In chemistry, you'll know it as relative atomic mass, but in physics, we call it nucleon number because it's just a quantity of particles. So what we can do is we can use these numbers to illustrate different isotopes using what we call nuclide notation. So carbon 12 looks like this, carbon 13 looks like this, carbon 14 looks like this. So they're all carbons, they all must have 6 protons, so they must have different numbers of neutrons, but carbon 12 is by far the most common found, but carbon 14 is quite useful to us to date things. Okay, so now we're going to start introducing a force that governs what goes on with a nucleus called the strong force. What we need to understand first is the nature of the strong force, or how it changes with distance. So you've already looked at how electric fields and gravitational fields work and how they change with distance. So we're going to do the strong thing with the strong force, but compare it to the electrostatic one. So the first thing to note is that it's not infinite range. It has a range of about 4 femtometers, or 4 times 10 to the minus 15 meters. So beyond that, it has basically no effect, which is why for a large amount of the time, we don't really think about the strong force, because it doesn't affect things until you get very close to the nucleus. But once you do get into the range of the strong force, you can see it is much, much stronger than the electrostatic force. So it's considerably bigger, which is why protons are able to be bound into a nucleus, because this strong force is what's holding them together. But the other thing to notice is that if they get too close, the strong force becomes repulsive and pushes them back apart again. So the force can change direction, and it keeps nucleons at a kind of a fixed separation inside the nucleus. Okay. So now we got an approximation for nuclear size. Let's look at how we would actually now go about calculating the radius of a nucleus. So what we've discovered is there's a relationship between nuclear radius and nucleon number. So that's what A stands for, nucleon number. So if you do the nucleon number, or the cube root of nucleon number, times the radius of a hydrogen nucleus, that gives you the radius of any other nucleus as well. And what that allows us to do is to start working out how dense a nucleus is, or how dense an atom is. So if we focus on a nucleus, so the mass of the nucleus is going to be the nucleon number times the mass of a nucleon, which protons and neutrons effectively have the same mass. The volume of the nucleus is going to be, if we model it as a sphere, it's going to be 4/3 pi r cubed, and we can put the r0, a to the cube root of a in instead of r. So if we want density, we're going to do mass divided by volume, and when we plug the mass of a nucleon in, and we plug the radius of a hydrogen nucleus in, what we can do is get an approximation for the density of a nucleus. And once we know that, because we know the radius of an atom is about 10,000 times the radius of a nucleus, we know the relationship between the volume of the atom and the volume of the nucleus, and therefore we can get an expression for the density of an atom, which is going to be 10 to the 12 or less, so about 2.3 times 10 to the 5. So still quite dense when you think about it, but that would be our atomic density. Okay, so next we're going to look at some of the other fundamental particles that make up our universe. We've come across protons, neutrons, and electrons, but there are many, many more than that, and we have different categories to describe how they behave. So that's what we're going to do next, and then we're going to use those particles to explain a few kinds of nuclear decay you've probably come across before. Okay, so first off, the class of particles we're going to talk about are antiparticles. So if we take the particles that make up atoms, they each have their own antiparticle. Most of the time their naming is very straightforward. It's an antiproton, antineutron, but for an electron it is a positron. That's its antiparticle. And what we mean by an antiparticle is it has the same mass as its particle pair. So a positron and an electron have the same mass, but they have the opposite charge. So a positron has a relative charge of +1. Now, once we stop thinking about just building atoms, there are large numbers of types of particles. And generally speaking, we classify them into 2 groups. The first group are called hadrons. So these are any particle that can interact through the strong force or the strong interaction. And to allow them to do that, they must be made of quarks or antiquarks. So the protons and neutrons we've come across already would be classified as hadrons. Leptons are particles that cannot interact through the strong interaction because they're not made of quarks. They themselves are fundamental particles. And things like electrons are a lepton, but so are muons or neutrinos as well. Okay, so what we're going to start thinking about is the quarks that we use to build our hadrons. So the first quark we use would be an up quark, the second one is a down quark, and the third one is a strange, and they have their all own antiquarks as well, which we have just a little bar over them. There are actually 3 more types of quarks, the top, bottom, and charm quark, but these are the ones that make up the majority of the hadrons, so we're just going to stick to those 3. So if you're a proton, you are made of 3 quarks, up, up, and down. So that makes proton something called a baryon because it's made of 3 quarks. A neutron is up, down, down, so it's also a baryon. It's got 3 quarks. An antiproton is the exact opposite of a proton, and an antineutron is the exact opposite of a neutron, and those would be known as antibaryons because they're made of 3 antiquarks. The other type of hadron is called a meson, which is a quark and an antiquark. We won't worry about those for now. Okay, so when we're building decay equations, what we've noticed is there are 3 rules that all nuclear equations have to obey. So the first one is something you'll have applied a lot of the time with electricity and other things. Charge has to be conserved in nuclear decay equations. But the 2 new ones that apply really just to particle physics is baryon number has to be conserved, which is essentially a way of measuring quark number, really. So 1 quark has a baryon number of 1/3. And we also have to conserve lepton number, so we can't lose our fundamental particles that are leptons either. And a lepton has a lepton number of +1. So you can see that if a particle is a baryon, it's going to have a baryon number of 1 because it's made of 3 quarks. And it would have a lepton number of 0 because it's not a lepton, it's a type of hadron. So what we can do is we can figure out the quark configurations of some other particles that we detect, one of which is a sigma++, which is a type of baryon, which is a subset of hadrons. And because it's a baryon, it's made of 3 quarks, and because it's ++, that means it has a relative charge of +2. So what that means is it's made of 3 up quarks, because when you do 3 times 2/3, which is the charge of an up quark, that gives you a charge of +2. Whereas down quarks and strange quarks have a charge of only 1/3. Okay, so now we're going to use that model we've built to start thinking about types of nuclear decay that you will have come across. So first of all, beta plus decay. What happens is a proton decays through the weak interaction, which is another fundamental force, and that produces a neutron, a positron, and an electron neutrino. Whereas beta minus decay, a neutron decays again through the weak interaction, produces a proton, electron, and an anti-electron neutrino. So the question at this point is, why are we getting these electron neutrinos or anti-electron neutrinos? Well, they're there to conserve lepton number. So they were actually put in there to explain some missing energy in our reaction. So that's why the model of a neutrino came about. But the rule you then designed to make the equations work is saying that lepton number must be obeyed. So you need, if you're producing a positron, you need a neutrino because that cancels out the lepton number. If you're making an electron, you need an anti-electron neutrino, again, cancels out the lepton number. Okay, so if we now think about that in terms of our quark model, in a beta minus decay, where we are producing an electron and a proton, what's happened is a down quark changed into an up quark. So it's changed from a neutron to a proton. Whereas in beta plus, a proton turned into a neutron, so an up quark changed into a down quark. Okay, so what we're going to have a look at doing is writing some decay equations for different atoms, essentially. So if we do the beta plus decay of oxygen 14, so that would look like this. So in beta plus decay, a proton becomes a neutron. So you can see that the proton number is decreased by 1, but we then produce a positron so that the charge is conserved, and we produce an electron neutrino to balance the lepton number. If we do the beta minus decay of carbon-14, we get the proton number increases by 1 because a neutron turned into a proton. We produce an electron to conserve charge and an anti-electron neutrino to conserve lepton number. Okay, so moving on to look at radioactivity. So all of the stuff we looked at so far is to model one decay. Now we'll model a whole system of atoms that are decaying. That's what radioactivity is. And we'll describe some of the properties we use to describe the behavior of materials. And then what we're going to do is start looking at how we can model the sample using some equations. So again, what I do, pause the video, work your way through section 6.4.3, fill in as much as you can, and then we'll review it so we can fill in the gaps in your knowledge. All right, so let's start off by defining the word random in the context of radioactive decay. Because what it means is that the time at which a particle would decay cannot be predicted, and there's nothing you can do to change the probability of it occurring. Okay, so that's what we mean by random. There is no way of influencing it when it will decay at all. So we just have to use statistics to model it instead. So radioactive decay can take 3 forms: alpha, beta, or gamma radiations, typically. So in terms of describing each of them, so alpha is the same as a helium nucleus, so 2 protons, 2 neutrons. It's highly ionizing, so 1 alpha particle can ionize something like 20,000 other atoms. But on the flip side, because it's so ionizing, it will not penetrate things. It will ionize stuff straight away and be blocked by very thin materials or even just a few centimeters of air. Whereas beta minus radiation is actually an electron, and the electron is at quite high speed, so it's fairly ionizing. I think it can ionize something like 200 atoms, something along those lines. Because it's less ionizing, it has some penetration ability, so it can travel through paper, for example, or a few centimeters of air, but it will be blocked by a thin metal sheet or a few meters of air. The final one, gamma, is very high energy electromagnetic photon. That's what gamma radiation is. But a photon can only ionize 1 atom, so it's very weakly ionizing. But because of that, it has a very high ability to penetrate through materials, and you need something like thick lead or concrete to be able to absorb or block it. Okay, so taking that forward, so using the penetrating ability, we can actually use that as a mechanism for identifying the radiation emitted by different sources. So the piece of equipment we're going to use is a Geiger-Müller tube, and to make sure our readings get rid of background radiation, we would take a measurement of background radiation before we even get our source out. Then what we'd do is we'd measure the number of counts we detect when our detector is right next to the source with no barrier, and I would measure it over a period of a minute and divide the number of counts by 60 to get the count rate in counts per second. And then what I'd do is I'd subtract the background count rate to get what we call the corrected count rate, or the count rate from our source. And I'd then repeat that whole process, but now with a piece of paper between the detector and the source. And then I would do the same experiment with aluminium foil as well. And so after we've done that, what we're going to look for is the barrier that makes the count rate drop significantly. So if a paper barrier drops the count rate significantly, we've clearly got an alpha source. If the aluminium barrier drops the count rate, it's beta minus. And if the count rate is still pretty high after the aluminium, we know we're dealing with a gamma source of radiation. But the thing I'm going to stick at the bottom is thinking about making sure this is done safely. The most dangerous type of radiation to us humans is alpha, because if we ingest it or inhale it, it's going to cause a heck of a lot of damage. So I would handle the source using gloves so that it doesn't get onto my hands, so that I don't eat any radiation later on. Okay. So what we're going to look at doing is modeling each of the alpha, beta, and gamma decays in terms of decay equations. So A is a symbol for nucleon number, Z for proton number. So when we have alpha decay, we're going to change the element, which is why it's gone from X to Y, and emit a helium nucleus. But you'll notice the nucleon number and the proton number on each side is the same. That's there to conserve baryon number and to conserve charge. If we do it for beta minus decay, we know a neutron turns into a proton. So proton number increases by 1, but nucleon number is still the same. But we produce an electron, so charge still balances. Gamma radiation, we do not have a change of element. We just have the nucleus de-exciting and emitting a gamma photon. And that's why gamma usually comes after alpha or beta or whatever other kind of decay it is, because those processes leave the nucleus in an excited state. And then when it de-excites, we get a gamma photon. So when we're modeling the decay, one of the things we often measure or want to know about our source is the activity. And what that means is the number of decays we get per unit time. So that unit of time might be a second, it might be per minute, it might be per year. For different sources, we use different units of time, but it's the number of decays per unit time from the sample, which is why we have to subtract background reading from our measurements. And then to model it using statistics and probability, we assign different elements and different isotopes a decay constant. And that is the probability that a particle would decay in the next unit of time. So maybe there's a 50% chance, maybe there's a 20% chance. For everything it's different, and by taking measurements, we figured out what these probabilities are. And what we can do is use those two things to relate activity to the number of undecayed nuclei we've got left. So the number of undecayed nuclei left is called n. So if we multiply that by the decay constant, we get an idea of, or a prediction of, what the activity will be. And as long as n is sufficiently big, that's a very good approximation. Okay, so the other thing we use to describe a radioactive substance, which you've probably come across, is half-life. So half-life is the time it takes the number of undecayed nuclei or the activity to halve, which is why it's called half-life. And it's tied to the decay constant. So the way we manage to get the decay constants is by measuring the half-life of different materials. So let's look at what we actually do to go about measuring half-life. So again, same procedure, we're measuring radiation, so we're going to need to measure background to start with. And then what we're going to do is I'm going to get a Geiger-Müller tube and attach it to a data logger. So anytime we're making measurements over long periods of time, we're going to want a data logger so a computer can do it for us. What we do is measure the counts over 60 seconds and calculate the corrected count rate. And we'd keep doing that. So for lots of periods of 60 seconds, we'd keep measuring what the count rate is. And we'd keep doing that until we've got a significant change in activity. So then what we do is you'd plot a graph of activity against time. So we would have measured the activity every 60 seconds, effectively. And what we do is we'd measure the time taken for the activity to fall to half of the initial value. And we would do that in 3 different sections of the graph. So I would pick 3 different starting values, 3 different points at which it's reached half, and therefore get 3 values of the half-life, and then so I can calculate an average. Okay, so what we're going to then look at doing is modeling how a substance changes over time. So these are the equations we use to describe the number of undecayed nuclei or the activity at different units of time. So because the rate at which it's decaying is tied to the number of nuclei, we get an exponential type relationship. So these are the equations we use to model it. And so you can see how this works. There's quite a nice way of simulating this using dice. So with a die, we say that when it becomes a 6, it has decayed, which means there is a 1 in 6 probability that a dice will decay with each roll. So that means the decay constant is 1/6. So each unit of time is one re-roll of the dice. So what we're going to do is we'll roll all of the dice, and then we will re-roll all of the dice that are not 6s. So then we've had 2 units of time, and we'll re-roll all of the ones that are not 6 again, 3 units of time. And what we can do is we can plot the number of undecayed nuclei against time, and what you'll see is it comes out as an exponential decay. So anything that's modeled with this kind of, just using this probability, we're going to end up with an exponential type decay. Okay. So the graph that we end up with from that experiment for either the number of undecayed nuclei or the activity looks like this. So it's the graph of an exponential decay. And these models that we've developed to model it are quite useful to us because they allow us to date very old carbon-based materials, and specifically carbon-based materials that have got their carbon from the atmosphere. So what we can do is we can measure the activity of a sample using a Geiger tube, and we can look up what the activity of carbon in the atmosphere is due to the decay of carbon-14. And then we take the equation for activity we've got, rearrange it to put in time, and then put in all our values, and we can get how long it is. So typically for carbon-14, the decay constant would be in years to the -1. So this equation will output a time in years. Okay, so what we're going to look at now is, again, still focusing on the nucleus of an atom, but look at how we can use nuclei to start generating energy, or look at how stars generate energy. So first, we're going to start off by looking at some of Einstein's most famous work, and then we'll start looking at how we can actually build plants and devices that can harness this kind of energy. So first of all, Einstein's equation to calculate the mass of a quantity of energy. So that's what his most famous equation is for, but most of the time we see it in a form which is not used for. So this equation calculates how much mass energy has. And so if you have energy quantity E, if you divide it by the speed of light in a vacuum squared, that tells you how much mass that energy has. So the more energy something has, the bigger its mass gets. That's what this equation tells you. So if in a nuclear equation the mass increases, the equation tells you that it must have absorbed energy. Whereas if in a nuclear equation you get this phenomenon where the mass decreases, and there are quite a few where that's true, what that means is energy gets released, and that's what's happening in a power plant. Okay, so there are some processes that make use of this equation. So the first process would be annihilation, where we take a particle and its antiparticle, and they produce 2 photons. So what we can do is we can do a calculation and go, well, okay, how much mass did we lose? Well, the mass of a proton and an antiproton. And we can plug that into the equation, and that would tell us the total amount of energy released. And that would be split in half, so each photon would get half of that energy. Whereas if we want to take a photon and produce an electron and a positron, we're increasing the mass, and we're increasing it by the mass of an electron times 2, because there's an electron and a positron. And again, we can plug that into the equation and work out how energetic our photon needs to be for this process to occur. Alrighty, so what we're going to take a look at is some of the terminology we use to describe the mass and energy to do with a nucleus. So when we talk about a nucleus, we can talk about its mass defect. So when you form a nucleus, what happens is its mass decreases. And the difference between the mass of all of the particles that make up the nucleus, and the actual nucleus is called the mass defect. So we've seen from the previous slide that if the mass goes down, that process must therefore have released some energy, and that's what we call binding energy. So the energy released when a nucleus forms is binding energy, or the energy you have to put back in to increase its mass again up to the value for the separate parts is also the same value. And when we're comparing the stability of different nuclei, what we compare is the binding energy per nucleon. So the total energy required to separate a nucleus divided by the number of nucleons inside that nucleus. Because what that calculates is how much work you'd have to do to take one nucleon out of that nucleus. And that's why it's a measure of stability. Okay, so what we can start thinking about now is how we select nuclear fuels. So if we plot a binding energy per nucleon versus nucleon number graph, it looks kind of like this. So at the top of this is iron 56. So that is the most stable nucleus you can have. So anything to the left of iron 56 is something we can get energy by fusing or taking two nuclei and combining them together. Anything on the right of iron 56, we can split one nucleus into two daughter nuclei and release energy. So that tells us what kind of materials we put in different types of reactors. So if we have, we're going to start by looking at a nuclear power plant which uses fission, and we can start working out how much energy is released from a nuclear fission process by thinking about the binding energy released. So if we compare the mass of the products before the nuclear equation and we compare it to the mass after the nuclear equation, we should find that some mass has decreased because it's emitted energy when that's why we've used it as a nuclear fuel. So that's another application of Einstein's equation. So the way we do it with a nuclear fuel is we bind a neutron to a uranium nucleus to form uranium-236. So 235 is the fuel. We bind a neutron to it, becomes 236. That then undergoes fission process. So by binding a neutron to it, we make it much more unstable, and it essentially we make it much more probable a decay will occur. And it splits into two daughter nuclei and also about 3 neutrons. So it varies slightly from reaction to reaction, but on average, we produce 3 neutrons. And if we can slow down those neutrons using a moderator, those 3 neutrons can bind to another 235 nucleus and start the process again. And we've managed to create essentially a chain reaction. Okay, so there are essentially 3 key parts of a nuclear reactor. There are the fuel rods, which contain, I think it's uranium oxide typically. It's not usually pure uranium, but that's what we put into our nuclear reactor as the fuel, and that's what we remove once it's run out. And then I mentioned a moderator a second ago. We use a moderator to decrease the kinetic energy of the neutrons because they can only bind to a nucleus when they're traveling quite slowly. And when they're slow, we describe them as thermal neutrons. So that's what we're looking for to make a chain reaction. And then finally, control rods. So we don't want our reaction to get out of control. So if every one reaction can produce 3, that's going to get out of control very quickly. So we have control rods which allow us to absorb some of the neutrons and keep it under control. Okay, so we've taken a look at the actual reaction we use to produce energy. What we're now going to look at is the problem, or one of the big problems with nuclear power plants, is that the waste they produce is radioactive, and we have to deal with that and store it in a way that we can essentially store it for thousands and thousands of years until it's safe. So the first thing is, when it comes out of the reactor, the waste is incredibly hot, and that's the first problem we have to deal with. And there's a very simple solution to that. We basically stick it in a pond for about a year, and that pond has a name, it's called a cooling pond. So that's what we do to, first of all, decrease its temperature and make it reasonable to start processing. Then what we do is we seal it inside a drum, and before we do that we usually vitrify it, which means we turn it into glass, but the reason we seal it is to prevent it leaking out into the surroundings, so that eventually blocks off alpha radiation. And the drum is usually made of metal, so that if it's sealed inside, we've now blocked alpha and beta radiation. To deal with gamma, we have again come up with a fairly simple solution. We stick it really deep underground and let the Earth absorb all the gamma radiation. So we don't put it near where there's lots of life. This is usually done in the middle of deserts or buried in salt mines, that kind of thing. But we bury it deep underground to absorb all the gamma radiation. Okay, so that's fission, which is what nuclear reactors do. Now we're going to take a quick look at nuclear fusion, which is what's happening in stars and is what we'd like to be able to do on Earth. So the problem with nuclear fusion in terms of recreating it is getting the temperatures or the kinetic energies to the level we need. So in a star, the nuclei all have incredibly high kinetic energy because it's really hot. And they have high enough kinetic energy that they can transfer it to electric potential energy, which means they can move, the nuclei can move close together even though they have the same charge. So they're increasing their electric potential energy and decreasing their kinetic energy, but they've got enough kinetic energy to get close enough for the strong force to bind them together. And that's when the process of fusion occurs. So that's, in a nutshell, the conditions that you need. It needs to be really hot, so the kinetic energy is really high, then you can get fusion to occur. Okay, so the fusion process involves, first of all, turning hydrogen into helium-3 and then fusing to helium-3 nuclei to make helium-4. So let's have a look at that stage. So here, two helium-3 nuclei look a bit like this. And we said they're producing helium-4, but we know if we just said we produce helium-4, we had 6 baryons on the left and we only had 4 on the right. So we clearly need to produce 2 more baryons up there. And we also have the problem we have a charge of 4 on the left and 2 on the right without the extra particles. So the 2 particles we need must be protons to make charge and baryon number balance. The lepton number is 0 on both sides anyway, so that's not an issue. Okay. So what we're now going to move on to is the medical physics part of the course. So looking at the different ways we can use physics to see inside the human body. So the first one we'll look at is X-rays, and then we'll look at CAT scanners, which is essentially advanced X-rays. So again, pause the video and work your way through this section and see how much you can do to start off with. Okay, so an X-ray tube is what we use to produce X-rays. So it looks something like this. Your diagram doesn't need to be exactly the same, but it needs to have the few fundamental parts. There should be a lead casing around everything. That's what's going to protect the workers from the X-rays. There should also be a glass, it's called an envelope or glass tube, that creates a vacuum inside so that as many electrons as possible can reach the target. You should also have a cathode, which would have a current passing through it. That's our source of electrons. And you should have a target with an anode. That's going to be, the anode's there to accelerate the electrons. The target is what's going to produce the X-ray beam that you can see there. So those are the fundamental parts. And you can see there's a little bit more to it than that in terms of how it works, but those are the key bits. So in terms of the mechanisms to produce X-rays, the first thing we do is make electrons flying through the tube. And the way we do that is by thermionic emission. So we make the cathode really hot by passing a current through it, and the electrons gain enough kinetic energy to escape from the material and are emitted in all directions. This is why we need an anode. So that's there to apply an electric field and make the electrons accelerate to high speed towards the target. This is where we start making X-rays. So the electrons collide with orbital electrons inside the target. They make them become excited. And when they de-excite again, about 1% of the photons emitted are the desired X-rays we want. And typically what we do is we then pass it through a filter to get rid of all the other photons we don't want. So the way an X-ray image works is using attenuation. So let's first define what that is. So it's the gradual decrease in intensity of radiation as it travels through a material. So that's what we mean by attenuation. So there are essentially 4 mechanisms that cause attenuation to occur. So the first is just called scattering, where an electron in an atom will absorb the X-ray, and then the electron will de-excite and emit the same X-ray as before, but in a completely random direction. So we lose our beam of X-rays traveling in one direction because they're emitted in all directions by scattering. The next is Compton effect. So again, they're absorbed by an electron, but they're then re-emitted as lower energy X-rays from that process. Then we have the photoelectric effect. So a free electron in some material absorbs the X-ray and gains enough kinetic energy to escape. And this is the main mechanism for attenuation in medical X-rays. And the final one is pair production, where the X-ray produces a particle or an antiparticle, so maybe electrons, positrons, that kind of thing. So these are the mechanisms for attenuation. So let's actually have a look at how we use that. So first off, we need to define a couple more things before we can explain how we then turn that into an image. So half-value thickness is very similar to half-life. So half-value thickness is the distance radiation has to travel in a material for its intensity or power per unit area to halve. And the attenuation coefficient of material essentially tells you the probability that an X-ray photon will be attenuated in the next unit distance. So you can see they're very similar to the way we model radioactivity. And what we can do is model the intensity of the X-rays using the initial intensity and the attenuation constant and the distance traveled in the material. And that's what allows us to produce X-ray images, because if we have a small amount of X-rays on the far side, we've gone through something with a high attenuation constant, maybe like a bone, or if we get a lot of X-rays coming through the other side, we know it's gone through something with a low attenuation coefficient, so it's probably muscle or something else. So simple X-rays are great for seeing bones, but what if in a CAT scan we want to see something that's not a bone? So when we're trying to look at organs with a CAT scan, the problem is a lot of organs have a very similar attenuation coefficient. So what we do is the organ we're interested in, we inject a contrast medium like barium or iodine, and that gives the target a higher attenuation coefficient, so we can see it much better under X-rays in terms of producing an image. Now, a CAT scanner is something we use to produce more detailed images when we really need a close look at what's going on. So what we have is an X-ray tube that rotates 360 degrees around the patient, and we have detectors that rotate with it that are always on the opposite side of the patient. So they're always detecting the X-rays that make it through the other side, and they measure the intensity of those X-rays and work out what they have traveled through. Then a computer takes the intensity readings and turns it into a 2D slice of the patient. So it tells us the different materials in that slice. And then what you do is you move the patient in and out of the CAT scanner, and it builds up a series of 2D slices, which if you want to, you can turn into a 3D image. Or as a doctor, you can look at each slice individually to look in really good detail. So let's talk about how we compare a CAT scan to a typical X-ray image. So they both have advantages, so both are currently used, but they both also have disadvantages, which we'll take a look at. So first of all, CAT scanners are very expensive. We're talking tens of millions of pounds, whereas an X-ray machine is relatively cheap. You're not going to pick them up for a couple of quid, but they are much cheaper than CAT scanners. The downside, again, of CAT scanners is you're in them for longer, so you get a much higher dose of radiation, whereas an X-ray is pretty much snap, like taking a photo, so you get a fairly low dose. As a patient, you're more inconvenienced by taking a CAT scan. It takes a lot longer. An X-ray can be done basically in the same time it takes to snap a photograph. On the flip side, with a CAT scanner, you get 2D images that you can look at from lots of angles and in lots of detail, whereas an X-ray, you get one 2D image from one side of the patient, so you can't get as much detail. Okay, so that's X-rays. Let's have a look at some other diagnosis methods, and specifically some methods that we use to look at the metabolic rate of cells. So the first one we use is called a tracer, and a very typical one would be technetium 99M. So the things that make it a good tracer, it's a gamma emitter, so it produces radiation that can be detected outside the body. The M stands for metastable, so the nucleus stays in an excited state for a period of hours. So that gives us time to make it, transport it to the patient and start taking measurements. But its half-life is only in the order of hours or days, so the patient gets a limited radiation dose. So the tracer produces gamma rays, so we need a gamma camera to start making images of the body. So the first thing that happens is the gamma rays are collimated, which means they pass through a collimator, which is basically a set of tubes. And only gamma rays traveling parallel to the collimator can enter the detector. So we essentially filtered out all the gamma rays which would mess up our image. Then what we do is the gamma rays are absorbed by orbital electrons in a part called the scintillator, which is usually a crystal. And when the scintillator electrons de-excite, they mostly produce visible photons. We then use those visible photons and they enter the photomultiplier tube, and they're absorbed by free electrons in a metal in the photomultiplier tube, and they gain enough kinetic energy to escape via the photoelectric effect. We then use an electric field to accelerate those electrons. They collide with electrons in other atoms. Those electrons are emitted as well, and you get a pulse of electrons that can be detected by a computer. So there are a lot of stages in there, but essentially what it does is it turns gamma rays into a pulse that can be detected by a computer, and then it's processed to produce an image. So that's a tracer and gamma camera. And the way we use them is we use them as a way of measuring cell activity. So what we do is we attach it to a molecule that will go to the cells with higher metabolic rates. And depending which cells we want to send it to, we attach it to different materials. So I don't know, if we want it to go to a bone, maybe attach it to calcium, or it depends what we're trying to do. Because cells with an unusually high metabolic rate will be a cancerous type, or we can see cells that are not performing as well as they should do. So maybe one of your kidneys is not working as well as it could be. But that's how we actually target it. We attach it to different molecules. That's the key. So the other way we can look at metabolic rate of cells is using a PET scanner. So this uses a beta plus emitter, and it's typically injected. And what happens is it decays and produces a positron, and that immediately annihilates with an electron to produce two gamma photons traveling in opposite directions. Then what we do is we use a gamma camera to detect those two photons and measure the time difference for detection and calculate the coordinates of their annihilation. And in terms of how it works diagnostically, typically it's attached to glucose or sugar. So it's taken up by cells with very high metabolic rates. So we can use it to investigate the brain, because a large quantity of the sugar that we eat goes to our brain. So we can use it to measure brain activity. But again, cancer cells also have a very high metabolic rate, so we can use it as a diagnostic method for cancer too. Okay, so that's PET scanning. Let's look at our last method of in diagnostic medicine, the ultrasound, and we're going to explain how that works, both to measure thickness, produce images, and also measure blood speed. So first off, what do we mean by ultrasound? Well, sound wave with frequency above the human hearing age, which for the average human is about 20,000 hertz. Gets a bit smaller as you get older, but that's how we define ultrasound. And an ultrasound emitter and detector uses the piezoelectric effect. So let's first explain what that is. So this effect is essentially, it exchanges energy between two forms. So if you apply an EMF to a material, it causes it to contract, or if you contract the material, it induces an EMF across it. That's the characteristic of a piezoelectric effect. So we can use that to produce sound waves. So what we do is we apply an AC EMF as at the resonant frequency of a piezoelectric crystal, and that causes it to oscillate with a very large amplitude, producing sound waves. And if we pick a crystal with a resonant frequency above 20,000, it produces ultrasound waves. But if the crystal itself is expanded and contracted by a sound wave, this induces an AC EMF, which can be measured. So the same device we use to produce ultrasound, we can also use to detect it, which is very handy. So there are a few different ways we can use ultrasound. The first two are type A and B. So A, we use to measure the thickness of things. So what we do is we send a pulse of ultrasound into a patient, and we display the detected signals on an oscilloscope. So if we send the ultrasound at a bone, some of it's reflected off the front surface of the bone, some of it's reflected off the back surface of the bone, and the time difference between those arriving back can be used to measure how thick the bone is. We can also use it to measure how thick your retina is, other things like that. So we can measure the thickness of a lot of stuff. The second type is the one most people have seen on TV or in the movies. So what we do is we plot reflected, or we use a computer to turn reflected intensity into an image. So what we do is we make high reflected intensity really bright and low intensity grey or black. So we can use it to see things like a baby or gallstones or things inside the human body which are reflecting a much higher intensity of ultrasound back towards us. So the last form we're going to look at in a second is blood speed, but let's first explain why the different reflected intensities tell us about the medium. And to do that, we first need to define acoustic impedance, the product of the density of material and the speed of sound in that material. So what it turns out is the reflected intensity of a boundary depends on the difference of acoustic impedance between the two materials across a boundary. So the bigger the difference, the higher the percentage that will be reflected. And can cause problems, and that's why if you go for an ultrasound scan, they have to coat you in gel, because it turns out air and skin have a very big difference in acoustic impedance. So if you were trying to send ultrasound from air into the skin, it would all be reflected and none of it would go into the human body. So the way they get around this is using the coupling gel, which has a similar acoustic impedance to skin, to replace the air gap. So the transducer is directly connected to the skin by the gel. So pretty much all the ultrasound waves go straight into the patient, which is much better. So the final way we use ultrasound is to measure blood speed, and we use the Doppler effect to do that. So we use a slightly different equation for the Doppler effect. The difference is from when you've seen it before. We've now got the speed of sound instead of the speed of light because we're using sound waves. We've got a 2 in there because the sound waves have to travel to the blood and are reflected off, so it's traveled double the distance that compared to when we did it before with the Doppler effect in space, where the light just comes from the star to us. And the cosine theta is there because the sound waves in the blood are not traveling in the same direction, so the cosine of theta is there to account for that. So if we can measure the Doppler shift in frequency, we know what frequency of sound waves we've used, we know what the speed of sound is, and we can measure what the angle is, and therefore we can calculate how fast the blood is traveling, so we can investigate whether there's a blockage in an artery which we need to deal with, for example. And that concludes Module 6 and the whole OCR specification.